Hello there, students. In this video, we're going to be applying Kirchhoff's circuit rules in a few examples. To start, let's take a look at this basic circuit and go over the symbols and notation. These jagged lines indicate a resistor. These parallel lines indicate a battery, with the wider line being the positive terminal. The blue line indicates the presumed direction of current flow. To start using the loop rule, we need to pick a point in the circuit to start at. I'll use this yellow ball to indicate where we're at in our circuits. Starting at the bottom left and moving across the battery from the negative to the positive terminal, we gain a potential V. Then, moving across the resistor following the direction of presumed current, we lose potential equal to the current flowing through the resistor times the resistance of the resistor, which we know is equal to a potential from Ohm's law. Then, we complete the loop and end back where we started, so all of these potential differences must equal 0. Using algebra, we can rewrite this, recovering Ohm's law itself. In most circuit questions, you're being asked to find the current, so we do that simple manipulation here to solve for the current. Let's step up the difficulty a tiny bit with our next circuit. Here we have two batteries as voltage sources V1 and V2. And two resistors labeled R1 and R2. I've chosen the direction of presumed current, not knowing the actual voltage supply of each battery. It is entirely possible that I've drawn the current in the wrong direction, but as long as we're consistent with our math and signs, it won't matter. Starting at the lower left for the loop rule, we cross the first battery, and not because we're following the current, but because we're going from the negative terminal to the positive terminal, we gain a potential V1. Then we cross resistor R1 going with the current, so lose a potential I times R1. Next, we cross battery V2 going from its positive terminal to its negative terminal, meaning we lose potential V2. Last, we follow the current through the resistor R2, so we lose potential I times R2. We complete the loop here, meaning all of this must be equal to 0. Doing some algebra and solving for the current, we find that the current is equal to V1 minus V2 divided by R1 plus R2. If it turns out that battery V1 is larger, then the current will be positive, indicating that I have chosen the correct direction with my current arrow. If it turns out that battery V2 is larger than battery V1, then my current term will be negative, meaning the current arrow is pointing in the wrong direction. So as long as we're correct with our signs and procedures, it doesn't matter which way we draw the initial current arrows, the final answer will tell us what direction the current truly is flowing in. Let's step it up a tiny bit more so we can start using the junction rule in our next circuit. Here we have two batteries, two resistors, and I've labeled 3 currents. Starting with the loop rule at the bottom left, we cross the first battery, gaining potential V1. Then we cross the first resistor, losing potential I1 times R1. Then we go down the middle, losing potential V2. Completing this small loop, we get our first loop equation. We can get another equation from the loop rule by starting at the bottom intersection. Going up the middle, we gain potential V2. Then we cross the second resistor, which has current I2 flowing through it, so we lose potential equal to I2 times R2. Ending up back at the bottom intersection, we complete our second loop equation. We can get a third equation by looping around the outside, starting at the bottom left again. Crossing the first battery, we gain potential V1. Going with the current across the first resistor, we lose potential I1 R1. Going with the current I2 across the second resistor, we lose potential I2 R2. Completing the loop, we have our third equation. We can also use the junction rule in this circuit. Let's take a look at the top intersection. I've drawn current I1 as going into this point, and currents I2 and I3 leaving that point. So for our fourth equation, the junction rule says current I1 equals I2 plus I3. Now we can use all of these equations to find expressions for our 3 currents. We want an expression for each current without any other currents in the equation, so this will take some algebra work. Using equation 1, we can add the term with current I1 over, and then divide by R1 on both sides to isolate current I1. Easy enough. Using equation 2, we can add the term with current I2 over, and then divide by R2 to find our expression for current I2. We have to use our junction rule equation, equation 4, to find an expression for current I3, since it doesn't appear anywhere else in our original 4 equations. Solving that equation for I3, and then substituting in the expressions for currents I1 and I2 that we found above, we get the following expression. From here, we can multiply the first fraction by R2 divided by R2, and the second fraction by R1 divided by R1 so that we can combine the fractions. Then, cleaning it up a little bit, we get this as our final result for current I3. Let's take a look at this same circuit again, except this time I've changed the initial directions of currents I1 and I3, leaving current I2 the same. We solve this one the same way, getting 3 loop rule equations and 1 junction rule equation. For our first loop, starting at the bottom left, we first cross the battery gaining potential V1. Then, because we're crossing the first resistor going against the drawn current, we gain potential I1R1. Then we cross the battery going from positive to negative terminal, so we lose potential V2 before completing the circuit. I'm going to let the animation play out now, but follow along to make sure you understand why each term in our equation has the sign it does. For the junction rule and the way I've drawn the currents, we have current I3 into the point and currents I1 and I2 flowing out of the point. I use the first equation to solve for current I1, the second equation to solve for current I2, and then the fourth equation, the one from the junction rule again, to solve for current I3 and simplify it with the same manipulations as before. If you go back and check the answers we had from the previous example, where currents I1 and I3 were reversed, you'll see that our answers differ only by a minus sign. That's because it doesn't matter how we draw our current arrows, as long as we're consistent with our arithmetic. Once we plug in numbers, if our current I1 is positive, then the arrow was drawn in the correct direction. If a current turns out to be negative in the end, then the current is going in the opposite direction than which we drew it. On to our last example. Here we once again have 2 batteries, 2 resistors, and I've drawn and labeled 3 currents. We start with the loop rules and then finish with the junction rule. I'll let the animation play out, but follow along to make sure you understand the final equations. Starting with our second equation, I'll solve for current I3. Then, using the third equation, I'll solve for current I1. Finally, I use the fourth equation, the one from the junction rule, to solve for current I2, and substitute in for currents I1 and I3 with what we found above. Simplifying with algebra, we find this final expression for current I2. I hope these examples helped you understand Kirchhoff's circuit rules, but if you have any questions, drop a comment below or head over to my Facebook page in the video description. Thanks for watching and learning about physics.